Welcome to This Explainer. Today, we're diving into a massive, kind of hidden challenge lurking right behind one of our absolute favorite clean energy sources. When we picture wind energy, we usually imagine these sleek, white turbines spinning gracefully against a blue sky, silently generating the green power we desperately need to fight climate change. But behind that pristine image, well, there lies an incredibly messy, highly complex industrial reality that the energy sector is honestly just now beginning to face.
It brings up a question that reveals a pretty stark irony. What actually happens to a wind turbine when it dies? See, wind energy is incredibly clean while it operates, but the giant blades themselves create massive, unrecyclable waste at the end of their lives. These blades, some of which are literally longer than a Boeing 747 wing, are absolute marvels of modern engineering. They have to withstand hurricane-force winds, blistering sun, and freezing rain, all while staying incredibly lightweight. But the very engineering that makes them so tough in the air, it makes them virtually indestructible once they're taken down.
So, 20. The average lifespan of a turbine is only about 20 to 25 years. Why does that number matter so much right now? Well, think about the massive boom in wind farm construction that happened globally back in the late 90s and early 2000s. Do the math, and you realize that a huge number of blades installed decades ago are about to become scrap very, very soon. We are standing on the precipice of a colossal wave of industrial waste, and we desperately have to figure out what to do with it.
To really wrap our heads around the sheer scale of this impending waste crisis, just take a look at the UK. Over there, wind energy accounts for a staggering 33% of all carbon fiber consumption. I mean, it is basically neck and neck with the entire aerospace and defense sector. We're not just talking about a few random pieces of plastic here. We're talking about a massive global supply chain of highly advanced composite materials that currently have a one-way ticket straight to a landfill.
Section 1. What makes blades so tough? The material culprit.
So why exactly does this green tech produce such stubborn waste? It all comes down to material science. Wind turbine blades are primarily made of FRPCs, which stands for fiber-reinforced polymer composites. Basically, you take high-strength materials, like carbon or glass fibers, and lock them inside a thermosetting polymer matrix, usually an epoxy or polyester resin. Think of thermosetting plastics like baking a cake. Before you put it in the oven, you've got liquid batter. But once it's baked, the whole chemical structure changes. The molecules form these cross-linked chemical chains. Once those fibers are locked into the resin matrix for maximum aerodynamic strength, you cannot easily unbake the cake to get your raw materials back. And while unbaking a cake is just a terrible idea in the kitchen, it's exactly what scientists have to figure out how to do right now.
But here's a detail I found totally surprising. The waste problem isn't just an end-of-life issue. 10 to 18% of the total blade weight is wasted during the manufacturing process alone, mostly through in-process waste, scrap, or defects. Add to that another 5% lost when blades are swapped out for upgrades, and finally another 5% during decommissioning. Combine this constant, ongoing stream of waste with strict new regulations in places like the European Union that heavily restricts sending these composites to landfills, and it means we urgently need an engineering solution. We literally cannot bury this problem anymore.
Section 2. 3 ways to recycle blades. The engineering solutions.
How do we break down the unbreakable? First off, we have to recognize that recycling a turbine blade isn't just tossing it into a giant bin. It is a highly complex, 5-stage industrial pipeline. It starts with precisely identifying the blade material. Next, you implement the actual recycling methodology to separate the fibers from the resin. Then, you recover and prep the derived products. After that, you have to estimate their value and transfer them to marketing partners. And finally, establishing a market presence so these recycled materials actually get purchased and used to build new things. It's an entire ecosystem that basically has to be built from scratch. Now, when scientists look at separating the fibers from the resins, that's step 2 of the pipeline we just talked about, they generally categorize the methods into 3 main branches: mechanical, thermal, and chemical recycling. Each of these branches uses a fundamentally different approach to break apart that baked cake analogy we talked about earlier. Let's break them down and see how they stack up against each other.
We really start to see the compromises here when we compare mechanical and thermal recycling. Mechanical recycling is basically the brute force method, literally shredding, crushing, or grinding the blades into fine powder or chunks. It's straightforward, sure, and the resulting material can be used as a filler in concrete, but the massive downside is that it severely degrades the structural strength of those incredibly expensive glass and carbon fibers. They become completely useless for high-strength applications. Thermal recycling, on the other hand, tries to save the fibers by using extreme heat. By reaching between 450 and 700 degrees Celsius, methods like pyrolysis or fluidized beds burn the resin away completely, leaving the fibers behind. But this method entirely loses the high-energy polymer, it degrades the physical attributes of cheaper glass fibers, and frankly, it can create extremely hazardous gases.
While thermal processing effectively burns away the problem, chemical recycling, which is sometimes called solvolysis, acts much more like a precision scalpel. Instead of heat, it uses specific green solvents and catalysts to carefully dissolve the polymer matrix. What makes this so incredibly exciting is that it keeps the recovered carbon and glass fibers neat, shiny, and fully intact. They maintain their long fiber extension and tensile strength, meaning they can actually be used in high-end structural applications. You could, theoretically, use them to build brand new turbine blades.
Section 3. The Energy and Cost Dilemma.
This data completely exposes the ultimate trade-off here: energy consumption. Mechanical recycling, the brute force grinding method, is actually incredibly energy efficient, using only about 3 megajoules per kilogram. But remember, the resulting material is super low quality. If we want those perfect, high-quality fibers from chemical recycling, the energy cost rockets all the way up to 91 megajoules per kilogram. That means chemical recycling requires up to 30 times more energy to perform than just mechanically grinding the blades up.
And as you might guess, this trilemma extends right into the economics. Basic mechanical grinding is relatively cheap, coming in at around $100 a ton. But as soon as you step up to thermal methods, like fluidized beds or pyrolysis, just to try and save those fibers, the cost absolutely skyrockets past $320 a ton. It's all due to the massive electricity and gas demands. Which brings us face to face with an unavoidable reality. You simply cannot get high-quality recycled carbon or glass fiber back without paying a massive penalty in both energy consumption and process costs. If you go cheap, you destroy the material's value. But if you want to retain the material's value so it can be truly reused, you have to pump massive amounts of money and energy into the recycling process. And ironically, that cuts right into the very environmental benefits the wind turbines were supposed to provide in the first place.
Section 4. Closing the clean energy loop.
So how do we merge the green energy dream with this messy industrial reality? This quote from the source research actually hits the nail on the head. Transforming RFPC waste into a valuable resource and closing the loop in a cradle-to-cradle way is critical. We absolutely have to get to a point where the wind energy industry isn't just taking materials, using them for 20 years, and then burying them. Overcoming the severe limitations of these chemical and thermal processes, making them cheaper and more energy efficient, maybe through emerging hybrid methods like microwave-assisted chemical recycling, is absolutely vital. That hopefully forward is quite literally the only way wind energy remains truly sustainable across its entire life cycle.
And that leaves us with a fascinating, honestly almost philosophical engineering paradox to ponder as we wrap up. As governments and corporations race to build more and more wind farms to hit clean energy targets, can we really call our energy future clean if we haven't yet figured out how to clean up the incredibly complex machines that generate it? The clock is ticking on those early turbines, and the materials science world is in an absolute race against time to find the perfect solution. Thank you so much for joining me for this explainer. Keep your eyes on this space because the future of renewable energy depends entirely on how we handle its waste.